we present NoodlePrint, a method for cooperative 3D printing with multiple robots using helically interlocked tiles. This work is a result of collaboration across Texas A&M University, the University of Texas at Austin, the University of Arkansas, and Monash University. In recent years, multi-robot 3D printing has been of growing interest, where multiple robots work together to print large objects without the need of assembly and can print larger objects rather than traditional 3D printing. However, just putting several robots together to print is not a simple task. Minimizing the time to print requires satisfying several competing factors, such as collision avoidance between robots, waiting time for the robots, and task sequencing. Our work draws inspiration from recent works that offer a special type of topologically interlocked cellular segmentation of parts to enable simple mechanisms for layer-wise cooperation across multiple robots. Consider a part with arbitrary geometry and topology to be printed with an arbitrary number of robots. There are two critical questions that currently remain unanswered in prior works on cell-based cooperative 3D printing. First, in what sequence do we order cells to be printed? Second, once the part is ordered to be printed, can we increase the amount of parallel printing that occurs? Our approach to answer these questions rests on three methodological pillars. The first is a recently introduced idea called helical interlocking, which enables the creation of interlocked geometries while maintaining the ability to allow for layer-by-layer multi-robot material extrusion. Using helically interlocked cellular structures as our geometry basis, we introduce a multi-nozzle path planning framework based on cell sequencing at each layer while avoiding collision. Finally, we explore how we can optimize the part orientation to better distribute workload and minimize the time the robots spend pausing. Let us first look at the idea of helical interlocking. Simply put, helical interlocking is a method for creating topologically interlocked tessellations by stacking cell transitive 2 honeycombs along a helical trajectory. As a result of stacking along a helix, we end up with a cell transitive 3 honeycomb with interlocked tiles. What is interesting about helical interlocking is that the parameters of the helical trajectory directly control the intensity of interlocking as well. This offers a unique design space for additive manufacturing, wherein designers can include mechanical behavior as an integral part of the manufacturing process parameters. Given a helically interlocked cell structure, the goal is to determine how cells should be divided across multiple nozzles at each layer, and in what order they should be printed. While there are prior works that have addressed this problem, they have been restricted to 2 nozzle systems. Our work seeks to create a generalized framework for part segmentation. In order to do this, we first assume that we are given a robot setup and a part to print. A cellularization can then be created by using the helical interlocking algorithm described earlier and obtained at a given layer, which respects the boundary of the part at that layer. Cells can then be divided based on the closest robot. This allows for us to create the interfacing complex, which are all edges shared by cells printed by different robots. To order the cells for printing, each robot has its own interfacing path, which is made up of all edges which are shared by that robot's cells and all cells not belonging to that robot. Each robot's interfacing path will be used to create the printing order of the cells. In this case, the interfacing path looks like this for robot 1, for robot 2, and this for robot 3. Together, they form the interfacing complex, which we use to create the interfacing and non-interfacing cells, by checking which cells are within a safe distance to the interfacing complex. We can then label each cell with whether it is interior or exterior, based on if they are inside the part we are printing or not. The reason we keep exterior cells is to create the interfacing complex and order cells for printing. The ordering can then be created, which goes hand in hand with our communication framework to avoid collision, which we call wait and go, where robot 1 prints its interfacing cells, then sends a go command for robot 2 to print its interfacing cells, and when robot 2 is finished, it sends a go command for robot 3 to print its interfacing cells. Once robot 3 finishes, it sends a command for all robots to print their non-interfacing cells. Once a robot has finished its cells for a layer, it waits until all cells are finished, and the process repeats for all subsequent layers. Our next and final step is to determine how to place a part in the working volume of the robots to minimize the time to print. To conceptualize this problem, imagine a 2-robot setup, and a simple part to be printed. What is the spatial configuration of the part, both position, meaning translation, and orientation, meaning rotation, such that both robots work at the same time as much as possible? This setup, for example, results in quite a lot of interfacing cells, which will result in a lot of waiting time at each layer. Another spatial configuration reduces the amount of interfacing area, but causes the robot on the left to print most of the part. The best spatial configuration is this, since it is the minimal amount of the interfacing cells. From this simple example, we demonstrate two things. We should try to minimize the area of interfacing cells, since that will always create idle time when printing. The other cause of idle time is unequal distribution of non-interfacing cells. The goal should be to evenly distribute the printing area between all the robots. To put these operations into practice, we define a measure for concurrence per layer, denoted as C, as the sum of all interfacing areas across all robots. This is added with the pairwise average absolute difference of the non-interfacing areas for that layer. Since we are dividing by the total cell area, the maximum value is 1 and the minimum is 0, with 1 being all printing happens at the same time, and 0 being robots never print at the same time. The goal is to maximize this concurrence measure, since we want the robots to work at the same time as much as possible. While concurrence is not a one-to-one map of the time to print, it's rather an estimation. The final concurrence measure is simply the sum of layer-wise concurrence measures. To get an intuition about this concurrence measure, suppose that we are printing a castle with 2 robots. The idea is to translate and rotate the castle until we find a placement and orientation of the castle that maximizes the value of concurrence, which in this case turns out to be 0.8. Note that the orientation makes sense because the symmetry of the part is down the axis formed by the interfacing complex. But what would happen with 3 robots? In this case, the best value of the concurrence measure is 0.65. At the optimal, notice that robots 1 and 3 work on the spires of the castle in the front, while robot 2 focuses on the back portion of the castle. What remains to be seen now is the effect of geometric parameters on the time to print. For this, we conduct various experiments to validate our algorithm. We first compare the relationship between the helix parameters and the optimum obtained. We next evaluate if the helical interlocking does provide increased cohesion between the cells through bending and tensile testing. Finally, we physically validate that we can print parts by printing several interesting geometries. For the numerical results, we tested approximately 100 samples at various helix parameters, which are the number of turns of the helix and the radius of the helix, as well as the cell size, which are all the independent variables. In each case, we minimize the concurrence and show the time and concurrence at the minimum, which are the dependent variables. What we observe in this case is, as the number of turns of the helix changes, there is not a significant change or grouping in the concurrence or the time to print. The same happens when we group all of the tests by the radius of the helix. There is no general trend in the coloring of the points. However, when we group by cell size, there is significant grouping as we color by the different cell sizes, meaning that if we print larger cells, we get a much lower time to print. And if we print small cells, we get a much higher time to print, but a much better concurrence measure, meaning the robots print more at the same time, but it takes longer for the robots to print. The reason for small cells taking longer to print is due to the increased move time that the robots have. The key finding from these numerical results is this: the cell size is the variable that influences concurrence and the time to print the most. The helix parameters, radius, and number of turns do influence both of these, but to a much lesser degree, with no noticeable trend. This means that the amount of interlocking, the helix parameters, can be freely adjusted without having a noticeable effect on the time to print. Next, we can look at the mechanical evaluation using helical interlocking. Let us look at some selected results from our over 200 physical experiments that we conducted. In this case, we are only looking at tensile testing. We first compare to the monolithic, which is the non-segmented piece. One prior segmentation method is chunking, which is planar cuts between volumetric segments. The low and high angle chunking performs poorly in matching the strength of the monolithic. We also compare to the Delaunay loft, which is what a prior work used on topological interlocking to segment for C3DP. This also performs poorly when compared to the monolithic. However, the helically interlocked tiles have similar maximum tensile strength to the monolithic. The high interlocking helically interlocked tiles particularly shows that higher interlocking increases the strength when comparing to the low interlocking helically interlocked tiles. Finally, we demonstrate that we can print multiple layer objects. Here are some examples that validate the ability of the NoodlePrint framework for cooperative printing. For more details, please see our paper. Thanks for watching.